Algebraic structures, lecture 2, cosets and homomorphisms. Let us start with the definition of a coset. Let G be a group and H a subgroup of G. Definition: for an element G in our group G, the set GH, which consists of all products of the form GH, G on the left, H on the right, where H is an element in our subgroup H, is called the left coset of H that corresponds to the element G. Notation: the set of all left H cosets in G is denoted in this way. So G modulo H on the right. So H acts on the right and we get left cosets. Lemma: let G and R be two elements in G. Then we either have that the corresponding cosets GH and RH coincide, or that they are disjoint, which means that the intersection is empty. Proof: assume that GH and RH have some common element. Let's call it X. Then we can write X as G times H for some element H in H, and also as R times H tilde for some element H tilde in H. If we multiply this equality, GH is equal to RH tilde, with H inverse on the right, then we get a cancellation here on the left, so we will get G is equal to R times H tilde H inverse. But H tilde H inverse belongs to H, because H is a subgroup, which means that we can write G as R times something in H. In other words, the element G belongs to the coset RH. And now multiplying with H on the right, we get that the coset GH is a subset of the coset RH. By symmetry, we also have the opposite inclusion, and therefore GH and RH are equal. Now we can similarly consider right cosets. If we have a group G and a subgroup H, then for any element G in G, we can define the right coset of H that corresponds to this element G as the set HG, which consists of all elements in the group G, which can be written in the form HG, where H is an element in our subgroup H. And the set of all right H cosets in G is denoted in this way. So this is G modulo H with H acting on the left. So H is on the left, so we get right cosets. Lemma: for two elements G and R in G, the corresponding right cosets HG and HR either coincide or are disjoint. And the proof is exactly the same as for the left cosets. Let us note that if the group G is commutative, also known as abelian, in other words, that the operation in the group is commutative, that is, that AB is equal to BA for all A and B, then the notions of left and right cosets coincide, because it doesn't matter on which side, on the left or on the right, we multiply, for any subgroup H in G. Now let us look at some examples. Example 1. Let G be the additive group of integers and H a subgroup of all even integers. Then the cosets G modulo H with H on the right, so the left cosets. There are only two cosets. One of them is the group H itself, and this is the set of all even integers. And another coset is the set of the form H plus 1. And this is exactly the set of all odd integers. So in this case, we have two cosets, even integers and odd integers. And this is a commutative case, so the left and the right cosets here coincide. Example 2, this is just a generalization of example 1. If we take the additive group of all integers and consider there's a subgroup consisting of all integers divisible by some positive integer n, so h is equal to nz, then the set of cosets doesn't matter left or right because it's a commutative situation. So we have exactly n cosets, and these are the following sets. So h then h plus 1, h plus 2, and so on, h plus n minus 1. Example 3. For any group G, if we take as H the group G itself, it's a subgroup, then both left and right cosets with respect to this H, this set contains only one element, and there is only one coset, and that is G. So both the set of left cosets of G modulo G and the right cosets of G modulo G, both these sets are singletons, and they actually coincide, and the unique element of that set is the group G itself. The other extreme example is that if we take any group G and the trivial subgroup H in G, which consists just of the identity, then both left and right cosets, they always coincide, and they contain all elements of the group. So the set of left and right cosets, these two sets coincide, and they both coincide to our group G. Example 5. For any group G and any subgroup H in G, the subgroup H itself is both a left and a right coset, which corresponds to any element in this subgroup. If you take H and multiply on the left or on the right with any element of this subgroup, we get exactly the subgroup as an outcome. So here is a more detailed example. Consider the symmetric group S3. So this is a group of all bijections from 1 to 3 to 1 to 3, and it has 6 elements. So the bijections which send 1 to 3 to 1 to 3, that's the identity, to 2, 1, 3, that's a transposition of 1 and 2, 1, 3, 2, that's a transposition of 3 and 2, 3, 2, 1, that's a transposition of 3 and 1, and then we have also 2, 3, 1, that's a cyclic permutation of 1 to 3, and 3, 1, 2, that's another cyclic permutation of 1, 2, and 3. Let's take as H the subgroup which contains the identity and the transposition of 1 and 2. Then the left coset of H with respect to the identity is H itself, because H contains the identity. And similarly, the left coset of H with respect to the transposition 1, 2 is H itself, because H contains this transposition. Now, if we take the transposition 3, 2 and multiply with H on the left, we will get this element and then the cyclic permutation 3, 1, 2. If we take the transposition of 3 and 1 and multiply with H, we will get this element, the transposition of 3 and 1, and the cyclic permutation 2, 3, 1. So if we take the element 2, 3, 1 and multiply with H, we will get this element 2, 3, 1 and the transposition of 3 and 1. And finally, if we take 3, 1, 2 and multiply with H, we get 3, 1, 2 and the transposition of 3 and 2. So these are the left cosets of H, and we also have the corresponding right cosets. Again, the right coset for the identity is H itself, because H contains the identity, and the right coset for the transposition 1, 2 is H itself, because H contains this transposition. The right coset for the transposition of 3 and 2 contains this transposition and the cyclic permutation 2, 3, 1. The right coset for the transposition of 3 and 1 contains this transposition and the cyclic permutation of 3, 1, 2. So the right coset for 2, 3, 1 contains this element and the transposition 3, 2, and the right coset for 3, 1, 2 contains 3, 1, 2 and the transposition of 3 and 1. Note that in this example, the right coset for the transposition 3, 2, which contains 3, 2 and 2, 3, 1, does not coincide with the left coset for this transposition, because that left coset contains 3, 2, so the transposition of 3 and 2, and 3, 1, 2. So this is 3, 1, 2, and here 2, 3, 1. So more generally, if we look at all the cosets, we see that Hg is not equal to Gh for any G which is not in H, in this case. Proposition. For any subgroup H of a group G, and for any element G in G, the map from H to the coset GH, which sends the element little h to G times little h, this map is a bijection. Proof. Of course, this map is surjective by definition because G times capital H consists of exactly such elements. To prove that it is injective, let us assume that GH is equal to GH tilde for some H and H tilde in our subgroup. If we now multiply with G inverse on the left, then G will disappear and we will get H is equal to H tilde. And this means that our map is injective, and so it's surjective and injective, and thus is bijective. Corollary: for any subgroup H of any group G and any element little g in our group, the cardinality of H is equal to the cardinality of the coset GH. And of course, this follows directly from the proposition, because two sets have the same cardinality if and only if there is a bijection between these two sets. Now we can use this to prove what is known as Lagrange theorem. So let's summarize what we know. If we have a subgroup H in G, then we can decompose G into a disjoint union of left H cosets or right H cosets. We can choose one of them. Moreover, all of them have the same cardinality. So we have G, we decompose it into a disjoint union of subsets, and all these subsets have the same cardinality. Corollary, which is known as Lagrange theorem: if G is a finite group and H is a subgroup of G, then the cardinality of H divides the cardinality of G. So indeed, G is a disjoint union of subsets, each of them having the cardinality of H. So the number of those subsets is exactly the cardinality of G divided by the cardinality of H, and is usually denoted in this way, and is called the index of H in G. So from this we have the formula that the cardinality of G is equal to the index of H in G times the cardinality of H, and everything here are integers. Consequences. Recall that last time, for every element A in our group G, we have defined the order of A, we denote it by O of A, in G as the cardinality of the subgroup which A generates in G. So this subgroup consists of all powers of this element A, so we take the identity, then A squared, A cubed, and so on, and also A inverse, A to the power minus 2, and so on. And of course, some of these powers may coincide. This, at the end, might turn out to be a finite subgroup of G. And the cardinality of this subgroup is the order of the element. From the previous slide, we immediately get that if G is finite and A is an element in G, then the order of A divides the cardinality of G. So the order of any element of any finite group divides the cardinality of the group. For example, we had this group, the symmetric group on 3 elements, which had 6 elements, the permutations of 1, 2, and 3. And here is a table of order of all elements in S3. So the identity element has order 1, that divides 6. We have 3 transpositions, 2, 1, 3, 2, and 1, 3. So these are transpositions. When they square them, they become identity. So their order is 2. 2 divides 6. And we have 3 cyclic permutations, 2, 3, 1, and 3, 1, 2. So they become identity only when we take them to the 3rd power. So their order is 3. 3 divides 6. There are no elements in S3 of order 4 or 5, because 4 and 5 do not divide 6. 6 divides 6, but still we do not have any element of order 6 here. Theorem. Let G be a finite group, and H a subgroup in G, and K a subgroup in H. Then the index of K in G is equal to the product of the indices of H in G and K in H. Proof. From the definition of the previous slide, we have that the cardinality of G is equal to cardinality of H times the index of H in G. We also have that the cardinality of G is equal to the cardinality of K times the index of K in G. And we finally have that the cardinality of H is equal to the cardinality of K times the index of K in H. If we plug in the third equality into the first one, we will get that the cardinality of G is equal to the cardinality of K times the index of K in H times the index of H in K. And comparing this with the second equality, we get that the index of K in G is equal to the index of K in H times the index of H in G. Next, let us talk about group homomorphisms. Let G and H be two groups. And in order to be more explicit, let us assume that the operation in G is star and the identity element is E, and the operation in H is diamond and the identity element is F. Definition: a map phi from G to H is called a homomorphism or a group homomorphism, provided that for all elements A and B in G, the following holds. Phi applied to A star B is equal to phi of A diamond phi of B. So in other words, phi maps operation star in the group G to the operation diamond in the group H. Example 1. For any group G, the identity map on G is a homomorphism from G to G. Then this condition is trivial. Example 2. For any groups G and H, the map that maps all elements of G to the identity element of H is a homomorphism from G to H. So in this case, this identity reads the identity in H is equal to the identity in H times the identity in H. And that's of course true. Example 3. For any group G and any subgroup H of G, the embedding of H into G is a homomorphism from H to G. So then this equality is just trivial because the map is the identity on the elements. Homomorphisms have two very special basic properties. Property 1, proposition, let phi be a homomorphism from a group G to a group H. Then phi sends the identity of G to the identity of H. Proof. In the group G, we have that the identity times the identity is equal to the identity. So if we apply phi to this equality, we get that phi applied to the identity times the identity is equal to phi applied to the identity. Now, since phi is a homomorphism, phi applied to identity times identity is equal to phi of the identity times phi of the identity, but now in the group H. And so if we combine this, we get that phi of the identity times phi of the identity is equal to phi of the identity now in the group H. If we multiply this with the inverse to phi of the identity on any side, we will get that phi of the identity is equal to the identity element in H. And this proves our proposition. The second basic property of homomorphisms is the following proposition. Let phi be a homomorphism from G to H. Then, for any element A in G, phi of the inverse of A is equal to the inverse of phi of A. Proof. We have that A times A inverse is equal to the identity in G. So if we apply phi, we get that phi of A times A inverse is equal to phi of the identity, and we know that phi of the identity is equal to the identity in H. Since phi is a homomorphism, we can rewrite phi of A times A inverse as phi of A times phi of A inverse. And so we get the equality that phi of A times phi of A inverse is equal to the identity in H. But we know that the inverse is unique in a group, so phi of A inverse must be equal to the inverse of phi of A. This is due to the uniqueness of the inverse. Altogether, we see that group homomorphisms are compatible with all of the group structure. So they map the operation in the first group to the operation in the second group, the identity in the first group to the identity in the second group, and the inverses of the first group to the corresponding inverses in the second group. Here are some other examples. Let n be a positive integer and k be one of the set rational, real, or complex numbers. Then we have the determinant map from the group of all invertible n times n matrices over K. So this is a group Gn and K, the general linear group over K of size n. And the outcome, so the determinant of an invertible matrix, is a non-zero number in our set of numbers. So it's K star, and it's a group with respect to multiplication. And this is, of course, true because the determinant of the product AB is equal to the product of the determinants of A and the determinant of B. That's a usual identity for determinants. Example 5 considers the dihedral group D2 times n of all symmetries of a regular n-gon inscribed in the unit circle in R2. Let us number the vertices of our n-gon in some way by the numbers 1, 2, 3, and so on up to n. Then, any symmetry, so any element in D2 times n, induces some permutation of the vertices. And the permutation of a vertices is, of course, then an element of Sn, because our vertices are numbered by the numbers from 1 to n. And this correspondence defines a homomorphism from the dihedral group D2 times n to Sn. So here's an explicit example how it works. So for instance, if n is equal to 3, then we have a triangle inscribed in the unit circle. Let's number its vertices 1, 2, and 3. Then the identity symmetry, of course, gives the identity permutation of the vertices 1 to 3. The clockwise rotation by 4 pi divided by 3 sends 1 to 2, 3 to 1, and 2 to 3. The clockwise rotation by 2 pi divided by 3 sends 1 to 3, 3 to 2, and 2 to 1. The reflection with respect to the horizontal axis, it fixes 1 and swaps 2 and 3. The reflection with respect to the symmetry line which goes through 2, it fixes 2 and swaps 1 and 3. And the reflection with respect to the symmetry line which goes through 3, it fixes 3 and swaps 1 and 2. So in this particular case, for n is equal to 3, we have that D2 times 3 and S3 both have 6 elements, and we have a bijection between the elements of D2 times 3 and the elements of S3. Next, let us talk about composition of homomorphisms. Let G, H, and K be 3 groups. Let phi be a homomorphism from G to H, and psi a homomorphism from H to K. Proposition: the composition of psi after phi, that's a map from G to K, it is also a homomorphism. Proof: let A and B two elements in G. Then, if we apply the composition of psi after phi to AB, then by definition this is psi applied to phi of AB. Since phi is a homomorphism, we can rewrite it as psi applied to phi of A times phi of B. Now, since psi is a homomorphism, we can rewrite it as psi of phi of A times psi of phi of B. And now we can use the definition of the composition again to rewrite psi of phi of A as psi after phi applied to A, and psi of phi of B we can rewrite as psi after phi applied to B. And this completes the proof of the proposition. So now we can sum up, then we have the following construct. So we have groups, homomorphisms between them. We can compose these homomorphisms if we have two homomorphisms such that the target group of the first one, so the codomain of the first one, equals the domain of the second one, then we can compose them. And also we have the identity morphisms for each group. And these datums satisfy the following axioms. The composition is associative whenever it is defined. And the identity homomorphisms operate as local identities. So if we can compose identity with some phi on any side, we will get phi. This means that we have the so-called category of all groups and group homomorphisms between them. But in this course we will not work with this category, so this is just for information. Finally, let us talk about the kernel and the image of a homomorphism. Let G and H be two groups and phi a homomorphism from G to H. Definition: the set of all elements A in G which ascend by phi to the identity of H is called the kernel of phi and denoted ker of phi. Definition: the set of all elements of H of the form phi of A, where A is some element in G, is called the image of phi and denoted im phi. For example, if we take the identity homomorphism on G, then the kernel of this homomorphism is just the identity element, and the image is the whole group G. Example 2, if we consider the determinant homomorphism from gln k to k star, then the image is the whole k star, because for any element in k star there is an invertible matrix with that determinant. And the kernel is exactly the subgroup slnk of glnk, so that's a special linear group. This is a group of all matrices of determinant 1. A basic property of kernel and image is that they both are subgroups. So let G and H be two groups, and phi a group homomorphism from G to H. Proposition: the kernel of phi is a subgroup of G, and the image of phi is a subgroup of H. Proof: so we prove the first claim, and the second one is similar. We already know that phi of E is the identity f of H. So phi, any homomorphism, sends the identity of the domain to the identity of the codomain, and so it follows that the identity of the domain belongs to the kernel of phi, by definition. If A and B are two elements in the kernel of phi, then phi of their product is equal to phi of A times phi of B, because phi is a homomorphism. Phi of A is the identity in H, phi of B is the identity in H, and then if it takes the identity and multiply with the identity, we get the identity in H. And this means that AB belongs to ker phi. So ker phi is closed with respect to product of its elements. Finally, if A is an element in ker phi, then we can write the identity in H as phi of E, and phi of E is phi of A times A inverse, of course. Since phi is a homomorphism, we can write this as phi of A times phi of A inverse. Phi of A is f, that's the identity in H, because A was assumed to be in the kernel of phi. And f times phi of A inverse is equal to phi of A inverse. And now if we read this through, we see that phi of A inverse is equal to f. So this means that A inverse is in the kernel of phi. So the kernel contains the identity, and it is closed with respect to composition and taking inverses. So this implies that kernel of phi is indeed a subgroup of G. Kernels and images are useful to detect injectivity and surjectivity of homomorphisms. Let G and H be two groups and phi a homomorphism from G to H. Observation 1. Phi is surjective if and only if the image of phi is the whole of H. This, of course, follows directly from the definition. Observation 2. Phi is injective if and only if the kernel of phi is the identity. That's less obvious. Proof. So, of course, we already know that the identity belongs to ker phi, so therefore, if phi is injective, then ker phi consists of the identity by definition. Conversely, let us assume that phi is not injective. So this means that we have two different elements A and B in G, such that phi of A is equal to phi of B. Then AB inverse is different from E, that's because A and B are different. At the same time, phi of AB inverse is equal to phi of A times phi of B inverse, because phi is a homomorphism. This is equal to phi of A times phi of B inverse, because phi maps inverses to inverses. But phi of A is equal to phi of B, so we can rewrite it as phi of A times phi of A inverse, and this is equal to the identity in H. So by definition, this means that AB inverse belongs to the kernel of phi, and that's an element which is different from the identity, and this means that Ker of phi is different from the identity. So this completes observation 2. And finally, the final property is the bijection which is induced by any homomorphism. So let G and H be two groups, and phi a group homomorphism from G to H. Proposition: the map phi, which sends the element x to phi of x, it induces a bijection, which is usually denoted phi overlined, from the set of all left Ker phi cosets in G to the image of phi. Proof. First of all, let us check that this is well defined. So if we have two elements A and B in the kernel of phi, and any element G in G, then phi of GA is equal to phi of G times phi of A. That's because phi is a homomorphism. This is equal to phi of G times F. That's because A is in the kernel. And this is equal to phi of G times phi of B. That's because B is in the kernel. And this is equal to phi of GB. That's because phi is a homomorphism. So phi of GA is equal to phi of GB. And this means that phi is constant on the elements in the set of all left cosets of G modulo Ker phi. And so we can define the induced map phi overlined. Phi is constant on the cosets, so we have the induced map from the cosets to the image of phi. And of course this map is surjective by definition. So let's prove injectivity. So assume that phi of A is equal to phi of B for some A and B in G. And on the previous slide we saw that this means that AB inverse is in the kernel of phi, and similarly one proves that A inverse B is in the kernel of phi. But then A times kernel of phi contains B, because A times A inverse B is B. And thus it coincides with B kernel of phi. So if two cosets have a common element, they coincide. So this means that phi overlined maps different cosets to different elements in the image, which means that phi overlined is indeed injective. So it's surjective and injective, so it is bijective. Some problems and questions at the end. Problem question 1. Prove with all details that for any subgroup H of G and any elements G and R in G, the fact that G belongs to Rh implies that GH is a subset of Rh. Problem question 2. Compute all elements in the set of left H cosets in S4, where H is a subgroup of S4 consisting of all elements that fix 4. Problem question 3. Let H be a subgroup of G of index 2. Prove that the sets of left and right H cosets in G coincide. Problem question 4. Prove with all details that the image of any homomorphism is a subgroup. And problem question 5. Prove that sending an element x to the power 6 gives rise to a homomorphism from the group G of all complex 20th roots of unity to itself, and compute both the kernel and the image of this homomorphism. Thank you very much, and see you next time.